Every night of your life, the moon has been watching you. From the moment you were born to this very second, the same face has been turned toward Earth. The same craters, the same seas of ancient solidified lava, the same pale, familiar landscape that every human being who has ever lived has looked up and seen. For thousands of years, we called it the moon, and we painted it, and we wrote poems about it, and we navigated by it. And not once, not a single time in all of human history before the 20th century, did any human eye see the other side, the side that faces away, always away, permanently turned from us as if keeping a secret. We gave it a name that stuck, the dark side of the moon. And in that name, we packed everything we felt about it. Mystery, concealment, the unknown, the idea of a hidden face, a world within a world that only the universe itself had ever seen. There are conspiracy theories about it, songs about it, films about it, an entire cultural mythology built around the simple, strange fact that the moon has a side it will not show us. But here is what nobody tells you at the beginning. The dark side of the moon is not dark, and the truth of what is actually there, the real science of what the far side looks like, why it looks so different from the near side, what it has told us about the formation of Earth and the moon and the early solar system, is stranger and more fascinating than any myth we ever invented to fill the space. This is the truth about the dark side of the moon, and it starts with a locked door that took us 4 billion years to open. Why does the moon always show us the same face? It is not a coincidence, it is not random, and it is most certainly not deliberate in any conspiratorial sense. It is physics. Elegant, inevitable, patient physics. The process is called tidal locking, and it is one of the most fascinating gravitational phenomena in the solar system. Here is how it works. The moon is not a perfect sphere. Like Earth, it has slight variations in density. Some parts are slightly denser than others. And in the early solar system, when the moon was young and its orbit was different from today, Earth's gravity did not pull on all parts of the moon equally. The slightly denser parts of the moon experienced a slightly stronger gravitational pull from Earth. Over time, over millions and then hundreds of millions of years, this unequal pull worked on the moon's rotation. It acted like a brake, a slow, invisible gravitational brake that gradually slowed the moon's spin. And then it stopped. The moon's rotation slowed until it matched its orbital period exactly, until the time it takes to spin once on its own axis became identical to the time it takes to complete one orbit around Earth, 27.3 days. Both, spin period, orbital period, the same. The result is that the same hemisphere always faces Earth, always, locked in place by 4 billion years of gravitational influence. This is not unique to our moon. Tidal locking happens throughout the solar system. Most of the large moons of Jupiter and Saturn are tidally locked to their host planets, and many exoplanets discovered orbiting close to their stars are tidally locked as well, like HD 1989733b, that glass-raining nightmare, always showing the same scorched face to its star. Tidal locking is the universe's way of creating permanence, of taking something dynamic and spinning and gradually, inexorably, bringing it to a kind of gravitational equilibrium. It took roughly 1 billion years for the moon to become fully tidally locked to Earth. 1 billion years of slowing, of settling, of gravity doing its patient, quiet work. And when it was done, the far side was sealed away, hidden not by conspiracy or design, but by the most fundamental force in the universe. But sealed away from our eyes does not mean sealed away from discovery, because in October 1959, humanity did something for the first time in its entire history. We looked. The Soviet spacecraft Luna 3 swung around the moon on a carefully calculated trajectory and photographed the far side for the first time. The images were blurry, low resolution by any modern standard, taken with cameras and film technology from the late 1950s, transmitted back across 40,000 kilometers of space. But they showed something, And what they showed immediately raised a question that has occupied planetary scientists ever since. The far side does not look like the near side. Not even close. The near side of the moon, the face we have always seen, is covered in dark patches. We call them maria, from the Latin word for seas. Early astronomers thought they might actually be bodies of water. They are not. They are vast plains of ancient basaltic lava. Dark rock formed billions of years ago when enormous asteroid impacts cracked the lunar crust and allowed magma from the interior to flood the surface and solidify. These dark plains cover roughly 30% of the near side. The far side has almost none of them. Less than 2% of the far side is covered in maria. The near side is relatively smooth in the large impact basins. The far side is almost entirely highlands, ancient, cratered, mountainous terrain, one of the most heavily cratered surfaces in the entire solar system. A landscape that looks like it absorbed every impact the early solar system could throw at it and kept every scar. Why? Why does the moon have two such completely different faces? It took decades of study and several competing theories before a consensus began to emerge, and the answer involves the very earliest history of our solar system. In the first hundreds of millions of years after the planets formed, the solar system was a violent, chaotic place. Asteroids and comets and planetesimals were everywhere. Collisions were common. Massive impacts were not rare catastrophic events. They were just Tuesday. The moon, newly formed and still hot, was bombarded relentlessly. But the near side and the far side experienced that bombardment differently. Earth, hovering nearby, acted as a gravitational shield for the lunar near side. Large impactors heading toward the near side were more likely to be captured by Earth's gravity or deflected before they reached the moon. The far side had no such protection. It absorbed the full fury of the early solar system's chaos. Impact after impact after impact, shattering the crust, building highlands from the ejecta of countless collisions, creating the battered, ancient, heavily cratered terrain we see today. And those impacts on the far side may have done something else, something that explains the difference in maria. The crust on the far side of the moon is significantly thicker than on the near side, in some places 20 to 30 kilometers thicker. When the great impact basins formed on the near side, the thin crust cracked and allowed lava from the lunar interior to flow through and fill the basins. Dark plains formed, maria. On the far side, the thick crust acted as a cap. Even when massive impacts created basins, the crust was too thick for lava to punch through. The basins stayed empty, dry, just cratered stone. Same moon, same impacts, different outcomes because of a difference in crustal thickness. That itself traces back to the asymmetric bombardment of the early solar system. Every crater on the far side is a record, a fossilized memory of 4 billion years ago when everything was violent and nothing was settled, and the solar system was still deciding what it wanted to be. But there is one feature on the far side that stands above all others. One structure so enormous, so ancient, so significant that it rewrote our understanding of what impacts can do to a world. It is called the South Pole Aitken Basin, and it is one of the largest impact craters in the entire solar system. Roughly 2,500 kilometers across. That is about the distance from London to Moscow, a single impact crater spanning that distance. It is also about 8 kilometers deep, and the walls around its edges rise to nearly 5 kilometers above the surrounding terrain. It was created by an impact so enormous, so catastrophically almost unimaginably large, that the object that made it was probably several hundred kilometers in diameter, a rock the size of a small country, hitting the moon at tens of kilometers per second. The energy released was so vast that it would have melted and vaporized enormous quantities of lunar material. Debris would have been flung across the entire moon. Some of it may have escaped the moon's gravity entirely and entered orbit around Earth, or even landed on Earth's surface. The South Pole Aitken Basin is so old that its exact age is difficult to determine. Best estimates place it at roughly 4 billion years, one of the most ancient structures in the solar system, and it sits entirely on the far side, hidden, unseen by human eyes until spacecraft began mapping the moon from orbit. But here's what makes this basin more than just a record of ancient violence. Scientists believe it punched deep enough into the lunar interior to expose material from the moon's mantle, the actual interior, rock from beneath the crust that formed deep inside the moon during its earliest evolution. If samples of that material could be retrieved and studied, they would tell us things about the moon's formation and interior structure that no amount of surface study could reveal. And in January 2019, China's Chang'e 4 mission landed inside the South Pole Aitken Basin, on the far side. For the first time in history, a spacecraft made a controlled landing on the lunar far side. It required a relay satellite positioned above the moon to maintain communication, because the far side has no line of sight to Earth, no direct radio contact. The satellite acted as a bridge between the lander and mission control. Chang'e 4 is still operating. Its rover, Yutu-2, has been exploring the far side of the moon since 2019, the longest operating lunar rover in history, sending back images and data from a landscape no human eye has ever seen directly. What it has found has confirmed some theories and complicated others. The basin floor contains minerals consistent with mantle material. The geological record is extraordinary in its complexity. Every measurement adds to a picture of a moon that is far more geologically interesting, far more scientifically valuable than its quiet, airless, apparently dead surface suggests. And lurking in the permanently shadowed craters near the South Pole, in regions where sunlight has not reached for billions of years, there is something else entirely: water ice. Confirmed by multiple spacecraft and missions, water ice trapped in the cold darkness of craters that never see the sun. Ancient water, possibly delivered by comet impacts billions of years ago, and preserved in the perpetual shadow of the lunar poles. Water is not just water when you are planning to return to the moon. Water is oxygen. Water is hydrogen. Water is rocket fuel. Water is the difference between a brief visit and a permanent presence. The far side of the moon is not just scientifically extraordinary. It may be one of the most strategically important pieces of real estate in the inner solar system. The dark side of the moon is not dark. It receives exactly as much sunlight as the side we see. It has days and nights just like the near side. During the lunar day, the far side is flooded with the same sunlight that illuminates our night sky. The name was always a metaphor, a poetic shorthand for hidden, for unknown, for the part of something that faces away from you and therefore feels absent, secret, unknowable. And for 4 billion years, the far side truly was unknowable, not just to humans, to everything. No observer existed to see it. No instrument existed to measure it. It turned quietly in the dark of the early solar system, absorbing impacts, building its cratered highlands, preserving its ancient geological record in a cold and silent museum. Then we arrived. And in 65 years of space exploration, from the blurry images of Luna 3 in 1959 to the rolling tracks of Yutu-2 today, we have gone from total ignorance to a detailed scientific portrait of a world we spent all of human history not seeing. That is an extraordinary thing. Think about what it means for a feature of our sky, something as familiar, as intimate, as personally meaningful as the moon, to have an entire hemisphere that nobody had ever seen. A face that was part of our world in every meaningful sense, shaping our tides, stabilizing our axial tilt, lighting our nights, and yet completely unknown. The far side of the moon is a reminder that the universe does not show us everything at once. It reveals itself in stages, in moments of technology and curiosity and courage, in the decision to build a spacecraft and swing it around a rock 384,000 kilometers away and point a camera at the unknown, in the decision to land on a surface with no direct radio contact, to trust a relay satellite above the horizon, to put a rover on ground no one had ever touched. These decisions are not just engineering achievements, they are philosophical ones. They are the universe deciding, through the agency of conscious, curious, endlessly reaching creatures, to finally look at itself from a new angle. We have spent thousands of years looking at the near side of the moon and finding meaning in it. We built calendars by it. We navigated oceans by it. We told myths about it. We fell in love under it. And all that time, 41% of its surface was turned quietly away, carrying its ancient craters and its thick crust and its billion-year-old impact basin and its shadowed craters full of frozen water, waiting. Not with impatience, not with any feeling at all, just waiting the way geology waits, the way physics waits, with the total indifference of something that exists whether or not anyone is watching. Until something started watching, until we built the instruments and launched the spacecraft and had the audacity to go around to the other side and look. And what we found there was not a conspiracy, not an alien structure, not the dramatic revelation that centuries of mythology had prepared us for. Something better. A scientific record of the solar system's violent birth, a geological library written in craters and basins and ancient lava plains, a source of water that might one day fuel the ships that carry us further. A landscape so old it makes our entire human story feel like a footnote. And a lesson, quietly delivered by a world that has been orbiting us for 4 billion years. The things we cannot see are not absent. They are just waiting for us to go and look.